Good morning. We are presenting on the Droplet Motion Image Processor. This group is from our software engineering class from the computer science department. 5 of us are in the group, however, only 2 of us will be presenting today, Simba and I. My name is Dania. So this project was brought to us by Dr.
There may not be one, huh? I would check with Macaulay in her office.
We have to start over. It's up to you.
Okay.
You want to go with that? Can I start over? Sorry.
We'll just switch places with
Okay, sorry about that. Good morning. Our presentation is on the Droplet Motion Image Processor. This is a project for our software engineering class. There are 5 of us in this group. This morning, Simba and I, Daniel, will be presenting. Our customer is Dr. Ock from the mechanical engineering department, and he desired something that would process his high-speed images of a droplet. So, in this presentation, we'll talk about the main objective, the specific goals, the system, and how we implemented the project. Okay, our main objective was to develop software that can process and analyze images at a high speed with a high-speed camera of a water droplet bouncing off a ratchet surface. Our objective was to minimize the complexity of processing the data, because what used to happen is that Dr. Ock needed 3 different pieces of software, MATLAB, Optimus, and Excel, just to process this data. So we are going to calculate the centroid, the velocity, and the acceleration of the droplet of water as it bounced off the ratchet surface. This is the experiment setup for Dr. Ock's experiment. Okay, so the more specific goals were to take the position or locate the position of the droplet as it falls. Now, we are looking at high speed, we are looking at images, so we have to tell the computer what to do. We had to also discern where on the plane that the droplet would land and where it would bounce off. We had to calculate the position of the needle, because the droplet comes from a needle. We also had to determine the edges of the drop and the location of the centroid as it bounces on the surface. So each image, we were given about 300 test images. Each image has a droplet located at different positions. We also had to calculate the velocity and the acceleration, and those results we had to output to an Excel table. We outputted using a CSV, a comma-separated file, which can be read in Excel, and we also had to complete the processing in a timely manner. Currently, the process that Dr. Ock used took approximately 5 minutes, and that was just to process the image. So that was just using Optimus. It didn't include anything, any of the calculation manipulations that he had to do with MATLAB and with Excel. We also wanted to make it easy for the user to use. So we wanted to make it easy for interaction, easy to understand, so that it wouldn't be too much of a complicated piece of software. Those are the high-speed photos we were given to work with. As you can see, you have the droplet. The resolution is not very good. It's in about 3 different colors, and so we had to find a way to be able to read to make the computer read what was in those pictures. Okay, so who is going to be using this piece of software? Dr. Ock, Dr. Gore, and whoever their research assistants are. So all the users are going to have the same privileges on the system. Everyone will be able to upload pictures. Everyone will be able to select the needle or the surface and the base image. So the functions of this project were to load and process the images, define the needle, calculate the centroid and acceleration of the frame, and output in each frame, and output all your results to Excel. And so basically what we did, we created a graphical user interface, that's what the user interacts with, an image loader, a binary image converter, and we output all our results to Excel. Simba is going to give you more specific information about how exactly the program works.
As you can see here, we have our initial base image loader. How this base image loader works is that Dr. Ock usually takes an image of the clear field without the droplet. So after he's taken an image of the clear field, we ask them to input this base image. What our program does is that we run through and process and discern where the bottom of the needle is and where the base is. We do this because this optimizes our process substantially. If we had to process this whole image from the bottom here and the top here, there's no need. The droplet is falling from the needle and it's going to be bouncing in between this space. So this helped us to optimize our system so that we could know the base was at the bottom and that we didn't have to do any extra processing. Also, you'll find that there's a slider here that allows the user to adjust the binary conversion, because sometimes the conversion might not look correct, as in you might have little black artifacts here which would give you erroneous data. So they can use the slider to kind of adjust things. So once they've input this base image and they know that, and our system records that this is where we're going to be processing, every picture after that, when we load all the ones with the droplet falling, we'll be processing just the space, and it'll be at the exact same binary conversion as this picture is converted. And then here is our image loader and inverter. Just a fun fact. Although right now Dr. Ock was using Optimus and it took about 5 minutes, we've run our program, putting out all the calculations and everything, and it runs in about under a minute to output everything. So that's substantially less. We're talking about 20% of the time of what was initially used or what was initially done. So what this does is now, after you've selected the base image, you then select a file, the folder in which you contain all the other images that were taken in that same session, because each session has got different base images. So as it processes, it simply runs through processing between here and here, converting that into a binary, calculating the central calculations, then outputting into a CSV file. And that's how it runs. And there's a little green bar kind of showing you what to do. So you just come in, you've selected your droplet images, run, and it's as simple as that. Outputs it to a CSV in the same folder. So this is the binary inversion. The reason why we utilize binary inversion is that, as you can see on the image, there's different scales of color. So you've got, it's darker here, it's lighter there. When you're processing images, that's a problem. It's a lot easier for us to simply decide either we want to process this or we don't want to process this. So the binary inversion allowed us to convert the pixels into, based on the gradient of the color, into black or white. That way, when we are processing, we're simply deciding if this is a black pixel, we're processing it. If it's not, forget about it. So this helped, again, this was part of the optimization process, making the image processing a lot faster. So there were some issues with the centroid calculation. For example, as the droplet would fall, in the early stages when the droplet falls, it becomes heavily deformed, because as the droplet falls, it deforms. And when that happens, sometimes you'd get some weird artifacts that some pixels, with some of the centroid pixels that we're using, would somehow randomly appear in random places. So like this here, this red one. So when that happens, that pushes the calculation of the centroid slightly off. And so we've been dealing with kind of trying to scrub the data to allow us to give clearer and more accurate centroid calculations. Although it wouldn't be too bad, like with this instance, most of the times we're looking at about 3 or 4 stray pixels. But that means that the centroid may be 1 or 2 pixels or 3 or 4 pixels also removed from where it's supposed to be. So that can cause our data to become a little off. So we're trying to figure out how to manage these outliers that are outside of the centroid and make sure that we are getting the most accurate value for where the centroid is. And then this here is what clean data looks like. Red for the outside of the centroid, and then we use that to calculate the inner part of the droplet. So These are the MATLAB results that Dr. Ock had given us that he had been using, and this is what the graph looked like as the droplet fell. They used the X and Z positions that they used are a little bit different from ours because we are just using absolute values from the beginning of our bitmap all the way down to the bottom. But what you'll find is when you see the next slide, which is our data, how similar it looks, and that we've been able to replicate the same data at 20% of the time. And here's what ours looks like. This is our output data to the CSV as we're measuring the time. The scale is a little bit different because we haven't scaled it down yet because we're just measuring from the complete set of all the pixels in the picture. But we were able to simulate the same results in a part of the time. So we've been able to simplify the process and we've been able to produce great results in a fraction of the time. So as I said, we simplified the user interface. What was a complicated research endeavor for Dr. Ock can now be something that you can literally hand to a research assistant, click these 3 buttons, and you get the results. Combines the functions of Excel, MATLAB, and Optimus into one program. It's a one-stop shop. Means, again, less chance of user error. When you're moving things from place to place, things will get lost, data gets lost, people get confused. When it's all in one place, it's a lot easier. There is a lot less room for user error. And our best part, the faster processing than Optimus and MATLAB. Any questions? Yes, ma'am?
Could you go back to the slide where you showed the water droplets, where you scrubbed the data? There you go. Okay. Yeah. Those are 2 different droplets, right? That's not.
Yeah, these are
exactly
2 different. Yeah, these are 2 different images. Okay. This one is probably just after the droplet had bounced off, and this one is still when the droplet is coming down.
So when you say you scrub the images to clean up the data, you don't mean you're not referring to the original image. That's not what you scrub.
No, we're scrubbing our own. Yeah, after we've done the binary conversion, after we've been doing the central calculations, and as it bounces, because the way our central calculation works is that we have to decide where the outside of the droplet is. So sometimes when you calculate the outside of the droplet, it places random pixels like this here and incorrectly guesses where the outside of the droplet is because we're using kind of where the black part is, and so sometimes it puts it wrongly there, and that's when we have to kind of try and run through the images that we already processed and try and clean that up again.
So when this is being used by, let's say, a research assistant, are they always running the images by you so that you can scrub the data? Or
No. This is all programmatic.
It's all programmatic.
It's all programmatic. Right? Also, what happens is after we've run the process, it outputs the images. It outputs a converted image. So a copy of the first. So let's say we had an image called image 1. It will output an image called image 1 BW, which means that it's got that section that we processed, converted, and you can actually look and see if there are any random pixels and kind of try and adjust from there. Because sometimes you can go back to the base image, adjust the settings a little bit so that the binary conversion is more accurate and gives you less erroneous data. And therefore, when you do the conversion again, check to see if you see it, like you saw the graph. If you can see an outlier, you can go back into your images and check if the images were processed properly.
I understand. I'm just trying to figure out the user friendliness of this program.
Oh yeah, the users would not have to deal with this. They wouldn't have to deal with this.
So the users not.
Yeah, they don't have to deal with the scrubbing. This is just what we've had to deal with to make sure that we're giving them correct results. Users do not have to scrub the data. This is done programmatically. We are working on trying to make sure that it's always correct every time that it's done.
This happens behind this field. That's what the user sees. The user will not see that this is happening until after the program has completed and they can check the folder.
Okay, so every single time a user runs data, you have to check for the data, or you're trying to manipulate the program so that it's fixed.
Yeah.
So that whenever the user uses it.
Yeah, that's what we're trying. That's what we're trying to do. We're trying to make it so that it's fixed every single time. They don't have to deal with anything. If there's any adjustment that needs to be made, the only thing that they need to adjust is the binary slider that then allows them to make sure that their images are if there's any kind of pixels that are out of the way, that they're giving them the correct image. Yes, sir.
On your picture you were just looking at, when you determine the red boundary, those values are stored in an array?
Yes, it's in a list. It's actually a list because we're using C#.
Okay. But they are stored adjacent to each other, correctly?
Yes.
Correct. And as far as removing the outliers, a simple algorithm would be go to the edge of your object, traverse it all the way around, and any pixel you didn't run into is an outlier.
Okay. We'll try and implement that. Mike is our heavy image processor. So, but also sometimes it's a lot simpler. It's a lot more difficult than
That's why I know it depends on how they're stored in array. And
Yeah.
stuff. You got to be able to go follow the path.
Yeah. That's it.
So first of all, I really appreciate as a primary customer. So for hardworking, and you actually contributed a lot. And in terms of this reducing time, and also I use just approximation to find the central. So you use the random, another algorithm given by the central, right? And only what I'm concerned is now, did you check the repeatability? How many times did you check your?
Mike has run it on different sets of data, and he said that the results have been just as consistent on all the different images that you've given us. He's also run it on some of those other, so not just this one data set that you gave us, but also on the other data sets that we give him. So it is repeatable, and it still does give us correct values. Yes, ma'am.
Yeah, is the software ready to be released, or you guys have to run more tests before?
We're still in the final testing stages, but we are delivering this software on Friday next week to Dr. Ock.
Boring or?
Arrange it to take over meetings and send them together with
Yeah.
time.
But yes, the software is, barring minor calculations and just outputting a few things, the software is complete, and we are ready to deliver it at the delivery date next week, Friday. Any other questions? Yes, ma'am.
Well, what is the name of the software?
We just called it the the droplet motion image processor. So pretty simple. We didn't think of anything crazy. Although our team name is rather interesting. We call ourselves